Over the next few lectures, we're going to start talking about performance. This is where we get in and integrate some of the various ideas we've been talking about in aerodynamics and propulsion and such to look at more macro level outputs of our aircraft. These would be things like range, which will be our focus of today, um, as well as things like takeoff and landing, climb, descent, and so on. Okay, so a second here. To start, we're going to talk about range for an electric powered aircraft. Range is a distance that the aircraft could fly, the maximum distance that it could fly. All right, so electric power is going to be a bit simpler, so we'll start with that, and then we'll discuss, a fuel-based airplane. Okay, so one way to think about this is for electric power, everything is coming from our battery. And so a key spec here is what's called the energy density. So I'm going to write EB, this is going to be the energy density for the battery. Okay, so this is something you'll hear a lot, in both papers and in the news as people are working on various battery improvements, is how much energy capacity exists per unit mass, right? Because we can make a bigger battery, but it's really that density, how much energy is available per mass that we care about, okay? So if I know the energy density of my battery, then obviously the total energy then is just energy density times the mass of the battery, right? So I could write this way. The energy I have available to me is that energy density battery times the mass of the battery, okay? So for a given chemistry that will give me some energy density, I can make bigger and bigger batteries. Of course, that makes the airplane heavier and heavier. And really what we should add too is an efficiency. It's not going to be perfectly efficient, though battery efficiencies are close to 1. Okay, so that's the energy that I have available. I then need to ask, well, how much energy do I expend? How much do I use? So how much energy do I expend? Primarily, this is going to come from the propulsion system. Depending on your aircraft, there may be other auxiliary systems, control surfaces, lights, other auxiliary systems that are powered. But the primary one is going to be propulsion. So how much energy do we use from our propulsion system? Well, another way to ask that is, what is the work that is performed? Work is, remember, a force times a distance. And so the force, remember the force, what force does our propulsion system produce? That's the thrust. And the distance that it's going to act over, well, that's the distance that we fly. That's the range. Okay, so we're simplifying a bit to assume that we're just going to be a constant thrust the whole time. Our max thrust, this is going to be our maximum distance by the range, okay? And that's in the ideal scenario. So that would be the work that we use, that's the energy expend. But because of efficiency losses, we need to divide this by the efficiency of the propeller, efficiency of the motor. Right? We divide, of course, because these are numbers that are less than 1, so it's going to increase the energy expenditure. All right, then for steady flight, thrust is going to be drag, so we could also write this way. And propeller and motor. And so that's efficiency of the propeller and efficiency of the motor. So if we use up all of our energy, the energy available is all expended, we could equate these two. So if I equate those two and then I solve for range, because that's what I care about here, right? I'm trying to figure out how far can I fly. I'm going to get this. The range is going to be the energy of the battery times the mass of the battery times eta, and actually it's going to be NB, NP, sorry, not N, eta M, all divided by the drag. And I'm going to call this whole quantity here just eta. That's the total efficiency of my whole system, right? Whole propeller, battery, motor, all together. Okay, so another way I could write this and that's really, this is it, but I'm going to run another way because it's going to more closely parallel uh, what we're going to do for the fuel burning aircraft. I'm going to multiply this by lift over weight, okay? And weight, I'm going to say is mg, right? So lift over weight, if it's steady level flight, those are the same. And m here is not the mass of the battery, this is the mass of my aircraft. And I'm going to call it, we'll call it the takeoff mass because we're going to again compare this to fuel burning aircraft. But for electric powered aircraft, that mass doesn't change. Takeoff mass, landing mass is all the same. But we'll just call it that. Again, we'll see later why. Just it makes it easier to compare. So if I put this all together, I'm just going to slightly reorder this. It's going to be the energy of the battery times G times eta times L over D. And then I've got this fraction of the mass of the battery divided by my aircraft mass. Takeoff mass, same thing, aircraft mass. All right, so this is my final equation here. G, of course, is a constant. But what we see here is really we've got trade-offs between three systems. That if we want to improve range, and this kind of highlights the multidisciplinary nature of aircraft design, I want to have good aerodynamic performance, right, a high L over D. I want to have an efficient structure. So this ratio, the bigger I could get it, the further I could go, right? Just like I want a big L over D, bigger range. I want this ratio to get bigger, meaning I want most of my airplane mass to be battery mass. Any mass that I have to use for just structure is a waste from this range standpoint, right? It's not helping me to go further. But of course, I'm going to need some structure to carry the battery, to carry all the systems in my airplane. But the lighter I can make that, so I don't have much excess mass beyond what I need for the battery, the better, right? I can go further. So this is how efficient my structure is. Right? So if I can get lighter materials that can provide similar strength, then that's going to be better. This is how efficient I am aerodynamically. And then this is my efficiency of my propulsion system. So range is kind of a balance between efficient propulsion, aerodynamics, and structures. This is why we have to consider the multidisciplinary nature. For example, if I tried to make an aircraft that maybe was really efficient aerodynamically, I may have it be, it may be structurally inefficient, or it may not be as propulsively efficient. And it's really kind of a balance between these that I need in order to fly far, for example. This one, there's not a lot I can do, at least from the aircraft design perspective. Of course, that's an area of a lot of active research and looking at various battery chemistries and such to increase energy densities. Okay, so let's now look at the same concept of range, but for an aircraft that burns fuel. Okay, so this is all our transport aircraft, of course. What does the range look like? So what is the primary difference? Well, one big difference that you may, that we would see with a fuel burning aircraft, of course, is that we are burning fuel, meaning that fuel is gone. Our airplane is actually becoming lighter as we go further, right? So the airplane mass is not the same at the beginning as it is at the end, whereas for electric power, it's going to be the same, right? But for fuel burning, a significant fraction of our weight, in fact, could be fuel, and so we're going to land much lighter than when we took off. So we can't use actually just a simple algebraic expression. We're actually going to need to use an integral because the weight is changing continuously throughout the flight. It's not just an energy density that we can multiply. So since we can't write the range as an equation or as an explicit equation, the integral, what we can write is our specific range, our range per, well, let me write it this way. Specific range. That's the distance I fly divided by how much fuel I'm using. Okay, and so I can write this, the distance I fly, the range per unit fuel burn, and then I can integrate across my flight to figure out the total distance that I flew. It's going to be easier if we actually divide both of these by time. So let's say distance per time divided by fuel used, oops, per time. Okay. Well, what is distance per time? That, of course, is just velocity. That's how fast I'm flying. And what's fuel burn per time? Well, this is what we did before, right? We were looking at we were talking about propulsion, mass flow rate, um, but we're actually going to be interested in weight, so we're going to multiply this by G. So we're looking at the weight, fuel burn in terms of unit weight per time. Okay, so that's my specific range, is how fast am I going relative to how much weight and fuel I'm burning per unit time. We can write this another way, though. Remember, we talked about specific fuel consumption last time. That was an efficiency of my engine. And that was equal to my fuel burn rate per unit thrust. Right? So if I use that, I'm going to substitute that in here at the bottom. I'm going to get that I'm going to just call this SR here. It's not a typical abbreviation. I just don't want to write it again. Specific range. That's going to be V divided by SFC times T. If it's steady level flight, then thrust equals drag, and the same thing we did before. And like before, we're just going to multiply and divide by the same thing into a steady level flight, lift divided by weight. Okay, so this is my specific range, and the reason I want to do that is now we want to get in terms of weight. We're going to integrate as my weight changes across time. Okay, so this is my, right, the top of this was distance, and now I can integrate this to get the distance. So my distance flown is going to be the integral of this expression here, right? V divided by SFC. I'm going to group these two, L over D, and then I've got 1 over weight. Okay, so I need to integrate this because the weight is changing. I'm going to go from initial weight to final weight, and I actually need a minus sign in front of my dW. That's because my weight is decreasing from initial towards final. So I'm going to put a minus sign in front here. So back up again, what we're doing here is that we can't calculate range explicitly or as a simple algebraic expression. We could calculate how much distance we were flying per unit fuel burn, and then we converted that in terms of weight, and now we're just going to integrate that weight from the start of my flight to the end of my flight, and that's going to tell me how much I flew. And so I can calculate it every little piece. And again, the reason we had to do that is because unlike the battery, our weight is changing because we're burning fuel. Our weight is changing at every instant in time, and so that's going to affect our range that can fly. It's not a constant weight. Okay, so to integrate this, we haven't really made, the only assumption we made so far is steady level flight. And we could in general integrate this if we know what our L over D, how it varies across the flight, our SFC, our velocity. And in general, one would do that. That would be the best way to do it if you had a given design. But here for sort of conceptual design, if we don't know the details of aircraft yet, we're going to make some additional assumptions. We're going to assume that these terms here stay constant throughout the flight. In other words, that we fly at constant speed, which of course is not exactly true, but the takeoff and landing part are going to be a very small portion of the flight for a long haul flight especially. And if we fly, we often want to fly close to constant Mach number, and if we're close to the isothermal part of the atmosphere, that means constant speed, so that may not be so bad. SFC will vary somewhat with altitude, but again, at this stage, we'll approximate it as constant. And if we're at constant CL, then our L over D will remain roughly constant as well. So this isn't too bad, again, for preliminary design. So if we pull all those out of the integral, we're going to get this is V SFC L over D integral, right this way, just dW over W. And then the negative sign is going to flip the limits of integration. Okay. And then if I do that, I just get V over SFC L over D times the natural log of W evaluated running out of space from initial to final, which again, if we write this one last time here, V SFC L over D, that's going to be the natural log. It's a initial minus final, but we can use the log rule, right? That's the same as dividing those two quantities. Okay, so that's what I do. So again, the assumption we had to make first was steady level flight, which is the same thing we did for battery one, so that's not a big deal. We assumed a few things were constant, right? We assumed constant speed or constant Mach number in the isothermal part of the atmosphere, constant SFC, and a constant CL, so that we get constant over D. Just as a side note, what that would mean, remember, I'm going to write this and then erase it, so I'm just put another color here. Just remember what the definition of CL is. We said we wanted to fly at constant velocity and CL, and let's say this is steady level flight, so this is weight. Okay, so if I keep CL constant and I keep velocity constant in that integral, then weight is changing. Weight's decreasing the whole time. That means I would have to decrease density throughout my flight, which means I would be climbing the whole time. That actually is optimal in the sense, and so this is what's called a cruise climb. You know, where you'd climb. It's not like a steep climb, but you'd climb slowly throughout the entire flight to keep yourself at the ideal CL. Because of air traffic control rules, we can't actually do that. You have to stay at sort of discrete levels, but often this is approximated where an aircraft will fly at a constant altitude for a while, and then maybe later, you know, as the weight is dropped, it's going to bump up to the next level, and so on, right? Especially for a long flight, that can be a significant benefit. Okay, so here's the formula. I'm going to do one last thing though with this formula before we finish, just to put it in a form that I think is, well, let me say this. This is probably the more famous version of the form. This is what's called the Bouguer range equation. I like to write it in a different form, one for the comparison, but I think some of these parameters are more fundamental. First, what we're going to do is we're going to write it in terms of the enthalpy. So you'll remember last time with propulsion, we talked about the efficiency and how it could be related to specific fuel consumption. So eta, we saw it was equal to V infinity times G. Well, I've just been writing V, so I'm just going to write it as V, SFC, and then the enthalpy of the fuel. So I'm going to take, see how we've got V over SFC here, we've got V over SFC there. I'm going to substitute that in. The other thing I'm going to do, which is just for convenience here, instead of writing initial weight over final weight, I'm going to write it this way. The initial weight is equal to our takeoff weight, which is our takeoff mass times acceleration of gravity. And the final weight is going to be our takeoff mass minus the fuel part times gravity. And I'm writing it that way just because I want to separate. It's a little hard to think about physically, you know, just initial versus final. It'd be easier to think about a fraction of fuel versus total. So I'm going to make those substitutions. All right, I ran out of space here, so I'm just going to I'm going to erase this stuff here just to make some room. Sorry about that. It's a bit messy here. Okay, let me carve out a little space here, put it in a different color so you know we're continuing. Okay, so once I make those two substitutions, this is my final expression. Again, this is not there's nothing more math here, just writing in terms of different variables. That's the enthalpy of the fuel times G times my propulsive efficiency, L over D, and then I have the natural log of 1 over 1 minus MF, mass of fuel, over my takeoff mass. Okay, so that's the final expression. Notice again, we have the same trade-offs, aerodynamics here, structural efficiency here, propulsive efficiency here, and this is something, G, we can't do anything about, and fuel, jet fuel, you know, there's not much we can do about that either. That's a given. Okay, again, I like this expression better than the other one because the enthalpy of fuel is a constant, right? So, you know, when you say jet A fuel or whatever, I mean, there are a few different variations, and there's you know, some biofuels and other things, but this is going to be something I can't do much about. So this is a constant parameter, whereas SFC actually does vary sometimes appreciably during the flight. But I think efficiency here is maybe a more fundamental parameter. So I like it in terms of this way. And also here, I like this ratio instead of just thinking about initial to final, because this is a ratio of how much of my airplane is fuel, right? versus a structure. So it's a little more fundamental as well. So similarly, we ideally want this to be really high, right? That my airplane is mostly fuel and anything else that's mass is very light, right? I don't want to have as much or as light of a structure as possible. But of course I do need some structure. Okay, so now I've got those two equations. Um, actually, so before we compare these two, uh, this is just an exercise. We'll actually do this in class, but if you're not going to be there in class, or you're not in this class and you just want to do this, this would be something good to try on your own. See if you can look at that equation. So go back to this equation and figure out how far could an airplane fly on a tank of fuel, right? With some reasonable assumptions given our best technologies. So just to get you started, the enthalpy of jet A, which is our typical jet fuel, it's 42.8, this is about 43 megajoules per kilogram. And this is a massive amount of energy, and this is what makes, our jet travel possible, is that these hydrocarbon fuels are just so energy dense. And this is a really great blessing thing that I like this, right? The energy is so dense. So we got tons of energy. Just to give you some idea, that's enough energy to take a kilogram of mass into orbit, right? So very energy dense. So that's about, let's say, 43 megajoules per kilogram. You know G. So you're gonna have to figure out what is an L over D. What's a reasonable L over D? The best we can do. What about efficiency? What's the best total efficiency we can do? What about mass fraction? How much of our airplane could really be just fuel, and how much structure do we need? Okay, so try to look at some data on that, see if you can make some assumptions. One hard part is that we generally can't do all of these best at one time, right? So if we try to make L over D really big or make the structure really light, then we can't carry big engines. If that's a really minimal structure, so our efficiency is going to be less. So there's going to be some trade-offs, but give that a shot. See what you get. And like I said, if you're going to be in class, then we'll do that in class, and you can wait till then. Incidentally, you'll probably find numbers that are really close to what the world records are on flight or range. Okay, so let's go back now. We've got these two equations. I guess I wrote them in the other order here. This is for the battery, and this is for the fuel burning, jet engine based aircraft. So let's break it down. And you can see that I've written them so they parallel each other pretty well. They both have this term that's a energy density thing, right? This is energy density of fuel, this is energy density of a battery. G is the same, of course. Eta, these are efficiencies of the propulsion system. L over D, right, this aerodynamics, and then they both have the structures term. And of course they look different because in this case, this is just, we just had to multiply a mass times energy density to figure out how much energy we had. Whereas in this case, there was a natural log because we had to do that integral because the mass was constantly decreasing. So let's do some comparisons. First off, let's look at efficiency. So jet engines, and this will, I guess, help you with that other question there. A jet engine is probably at best around 40, maybe close to up to 50, somewhere in the 40% efficiency. Whereas an electric system can be about twice that. Our best electric systems can be about twice as efficient as our best jet engines. So there's an advantage here. However, jet engines have an advantage on this term, the structural efficiency. And that's because as we use up our battery, even though we're using up the energy in the battery, we still carry it with us. So we're carrying this mass the whole way through, even though as energy depletes, it's not as useful. Whereas for the fuel burning aircraft, as we burn fuel, that fuel's gone, right? So airplane's becoming lighter and lighter, and it's becoming more efficient because we're not carrying that fuel with us the whole time. So this term actually can be larger than this term is for electric aircraft. I have a plot of that in the text if you're interested on some different assumptions. But both of these are relatively small. So like this one is for jet engines a bit worse, but this one's a bit better. And of course, the aerodynamics, aren't necessarily, of course there are secondary effects, but we can do about as well in either case. The big difference by far is this term here, energy densities. We already talked about fuels, hydrocarbon fuels here. Jet A is going to be about 43 megajoules per kilogram, whereas our best batteries, we typically hear them in terms of watt hours per kilogram. So let's say our best battery is around 300 watt hours per kilogram, which is about, if you convert that to megajoules, about 1 megajoule per kilogram. So jet fuel is about 40 times more energy dense, right? And that's why, that's led to the success story of jet-powered aircraft, that we can fly these large distances, and how great that is, right? That we can fly these across continents, across oceans. It's amazing. With electric aircraft, we can't get anywhere near that range, right? We're 40 times less energy dense. So it's, I mean, we're a long ways away from replacing, at least entirely, the fuel burning systems of transport aircraft, but on shorter range flights, electric power is making great strides. And in the inroads, there's a lot of interest in these short flights, within a region, within cities, even parts of states and things. A lot of these short haul flights actually make up a significant fraction of all our flights. It's appealing because, of course, the electric then, we don't have emissions, at least not at that spot, right? So we could potentially then use renewable sources to generate electricity. It could be quieter, they're generally cheaper, less moving parts, and we can scale them down to smaller sizes, which is really nice for doing things like actuating them, distributing propulsion. So there's a lot of opportunities there. Okay, so I'm not going to go through any equations here. I just want to mention this concept. Range, right, is distance that we fly. And so another metric we think about is the time of flight, and we call this endurance for an aircraft. And designing an aircraft to fly for maximum range, say, is not the same as flying it for maximum endurance. Right? One means I want to design my aircraft to fly as far as possible, and the other says I want it to fly as long as possible. While those sound similar, they actually lead to some different design decisions, and we'll talk about a little bit about that in a second. Okay, but so there are equations for that in the text if you're interested in, but it's really sort of the same process, right? Just in terms of time as opposed to distance. So the last thing we're talking about is with respect to range is what speed should we fly at? What's the optimal speed for these different objectives? And another way to say speed, of course, is lift coefficient. We've already written this equation once, but I'll write it again, right? Lift, and our lift is generally going to be our weight for steady flight. So when we talk about optimal speed, maybe a more fundamental way to say that is optimal lift coefficient. So for a given airplane, not talking about changing the aircraft design, which of course could enter in, but even for a given airplane, if I want to fly at my speed for maximum range, or I want to fly at speed for maximum endurance, or I want to fly at speed at maximum L over D, these actually are generally different speeds, right? So the speed that's going to allow me to fly the furthest is not the speed that's going to allow me to fly the longest. And that's not necessarily the speed that's going to allow me to fly my max L over D, which is a metric we've been kind of using often up until this point. They're actually different. There's some equations in the book. You have to be a little careful with them, right? So there's some analytic formulas, but we have to make some assumptions. And there's one that's assuming constant thrust, which roughly corresponds to jet engines, because the jet engine, the thrust is so large. The inlet speeds are, or let's say it this way, they don't vary a lot with the flight speeds. So you could think of them as roughly constant thrust with respect to speed. They're not exactly, but that's, if you assume constant thrust, we can derive some analytic formulas. Versus constant power, right, which is electric power. Right? The power doesn't change with speed, for example. That's what I mean by constant power. If I go faster, slower, my battery still has the same power available. Whereas the opposites are true, right? So for electric aircraft, the thrust tends to vary quite a bit. Whereas for jet engine, while the thrust is relatively constant, the power requirements change quite a bit. These are just idealizations, and they're useful to kind of get some rough formulas, but you can see the book for details. But I would say the more important point here is the principle that these speeds are different. And what you will find is that the speed for maximum range is going to be faster than the speed for maximum endurance. Okay, so this way, speed for max range is greater than the speed for max endurance. This one is not too hard uh, to understand, right? Because endurance, that's just time. Well, that's going to be distance, which is range, divided by speed, right? So um, whatever speed maximizes this range, if I fly slower, right, if I bring this denominator down, that's not going to change my range, my maximum range by a ton, but it's inversely proportional to speed. So bringing that range down is going to bring up my endurance. So maximizing endurance, again, maximizing the time I fly means I'm going to fly at slower speeds than my speed for maximum endurance. So where does max L over D occur? It generally is somewhere in between these two. One way to think about this, let's say I've got this plot, right? This is a plot that we've done several times in this class and used early on to maybe help design vehicle, right? So I've got a plot like this. Aerodynamically, I may want to fly at the speed for max L over D. But if I want to fly for maximum range, it's generally going to occur at a faster speed. Why is that? Well, range, of course, is going to be directly related to speed, right? If I fly twice as fast, I will go, I can go twice as far, everything else being equal, right? But my L over D is not going to fall as quickly. So if we go back and look at the equations for range, for example, these kind of equations, right? They've got an L over D term here. That's going to be my range. And then if I multiply that, well, yeah, so if I think about how fast I could go, to go faster, well, actually, let me say it this way. If I go faster, I'm going to sacrifice some L over D, right? So these equations would predict I couldn't go as far. But I'm going faster. And so I more than make up for that. So I am burning fuel at a faster rate because I'm not at this ideal speed here, but because I'm going faster and that goes linear, this drop off, by definition, the maximum over D is going to be kind of flat at the top. So if I go a little bit off of that, I don't give up very much, right? That's just the definition of an optimum, that it's going to be flat at that point. So I don't give up very much if I just go off a little bit, but my speed is going to affect how far I go, directly, right? So going faster, well, so let me just say it this way. This one is always true. In general, my max L over D is going to occur somewhat between those two. So my slowest speed is going to be my maximum endurance speed. It's going to keep me aloft the longest. I'm going to be able to spend the most time in the air. My max L over D is going to be somewhat faster, and my maximum range is going to be somewhat faster still. Okay, and again, in the text, you can see some numbers that kind of give you some idea, again, for some idealized assumptions, but yeah, it's something that you can take a look at. Okay, so I think we're going to wrap that up with right here. Next time, we're going to do a kind of a quick discussion on some other areas of performance. We'll talk about climb and descent and turning, but we'll keep this one kind of focused on range. So we'll see you next time.